Did you know that approximately 1.6 tons of plastics are transported by the help of rivers? It is estimated that in 2016, over 150 million tons of plastic circulated in the marine environment. My name is Raquib, and today I'm here to talk about an issue that concerns every single living being in this planet. The study that I'm about to present focuses on getting a better understanding on how floating plastic debris is transported in the rivers by undertaking well-controlled lab experiments. This should help give an insight into the possibility of using low-cost, eco-friendly plants which require little or no maintenance to trap floating plastics in river system. Let's look at the problem in hand first. From 1950s to 2018, plastic production rapidly increased from 1.5 million to 359 million metric tons. Here, cumulatively, 7,800 million metric tons of plastic waste were produced till 2020, but only 1,000 million tons were recycled, proving that not all waste are handled and recycled properly and therefore end up in oceans. The different sizes and shapes of these mismanaged waste causes various adversities. Firstly, the increasing rate of ingestion of plastics by marine animals cause them to have poor health, reproduction, and behavior. Also, since plastic pass through food chain, non-direct consumers are affected too. Secondly, marine animals like fishes and turtles often get entangled in plastics, causing injuries to health and even suffocation at times. This is more common in oceans than in rivers. Thirdly, chemical leaching and accumulation causes breakdown of plastics into fragmentation and release of toxins. This affects the animals which feed from water. Fourthly, breakdown of plastics into microplastics due to mechanical and UV forces are problematic since these are found in food and compromises health and food security. Such wastes are hazardous. Finally, us humans rely on water for consumption and daily household activities. Consumption of contaminated water causes waterborne diseases which can even be fatal. Economic losses due to ship damage, tourism losses due to unaesthetic views, excessive flooding due to clogged drains, and other mentionable impacts of plastics. Rivers form dominant pathways for the plastic waste to transport from one place to another. 15% of all the plastic waste in ocean is transported by rivers. There are various sources that contribute to the mismanaged waste in the rivers, such as shipping activities, surface runoff from agriculture and industrial areas, fisheries, beach litter, and many others. Direct dumping of plastic waste into water bodies is also seen in less developed countries. For example, in my country Bangladesh, majority of the plastic found in rivers are household and industrial wastes. While considering the fate of plastic, sinks is important, which depends on plastic characteristics such as types, shapes, sizes, and density. The plastic either floats on the surface or right below, or it can even sink to the bottom of the ocean bed. In addition, owing to climate change resulting in increased frequency and magnitude of extreme rainfall, surface runoff, and subsequent flooding, the challenge of floating plastic transport is even more important, and ways to study and contain this becomes urgent. For this experiment, floating plastics were only considered as they are easy to spot and can be removed without much hassle. Processes such as transportation, accumulation, and degradation affect the fate of plastics. Moving on to the experiment, to understand the flow of plastics in the lab and how it interacts with vegetation patches, a variable called transport capacity was used. Transport capacity in rivers can be defined as the total amount of sediment a stream can transport, but as in our case, as we are considering plastic, it is the amount of plastic that is being transported. Furthermore, to understand the effect of the vegetation patches on the flow of plastic, transport velocity and efficiency were used. Transport velocity is defined as the speed at which the plastic moves between two different points, whereas the transport efficiency is how fast the speed of the plastic decreases. The velocity and efficiency were calculated using the given formulas. To understand the effects better, well-controlled flume experiments were conducted in water engineering lab in the University of Glasgow using different density vegetation patches. These vegetation patches have a variable amount of plastic rods that help vary the density. By using a ruler, the diameter of the plastic balls were measured and a weighing machine was used to measure them in grams. 5 plastic balls with increasing diameters and weights were used. Each of the ball had a mark on the top and bottom so that it was clearly visible while taking the reading. Also, a camera was used to record the transport process along the flume. A stopwatch recorded the time it took to travel from one point to the other. As it can be seen in the picture provided, the flume was set up in a similar way. The in-stream vegetation patches were placed in a fixed location F. It was made sure that the plastic balls were released from location at D. The plastics were released along the center line. Times were recorded when the plastic ball first crossed location B and the unobstructed velocity was calculated. From location B to C, the plastic achieved an obstructed velocity since it came in contact with the vegetation patch. The camera was placed vertically above the flume to record all the motion for later analysis. A sample of the recorded video is provided here to show how the experiment was conducted in the lab. From the table provided here, we can see the different diameters and weights of the plastic balls that were used for this experiment. I've conducted multiple trials for the different vegetation patches. The trials showed various results upon interaction between the balls and the patches. 3 outcomes were visible. The plastic would pass by without any contact, or it would bump on the vegetation patch but still continue on its path, or would come to a complete halt after interaction with the simulated vegetation. The times that it passed by without contact was disregarded as it did not contribute to the objective. The outcomes are presented using pie charts. For the most dense vegetation, we can observe that the chance of getting blocked is very low. There is still a chance of using these vegetation patches as a method to trap plastic waste. For the most dense vegetation patch, the biggest plastic object did not get blocked. The same can be seen for the biggest object when it interacted with the medium dense patch of vegetation. For the lowest density vegetation, neither of the 2 biggest balls got blocked. Thus, if blocking was the intention, we can either block plastics of a diameter smaller than 7 cm or use vegetation patches with a higher density. From the pie charts provided here, it can be seen that the least dense vegetation patches were the best choice for this objective, although it could not block the 2 biggest objects, but when it came to interaction with bouncing off, it showed a high probability of happening. Also, out of all the 5 sizes of plastic, the smallest is blocked the most. Throughout the whole observation, mostly the plastic came in contact and bounced off regardless of the density and the vegetation or the size of the plastic. A significant change in the speed of the plastic is seen. The kinetic energy was calculated using this information. It was understood how efficiently the energy of the plastic objects decreased. This can all be seen in the charts provided below. For each of the different plastic objects, 12 readings were taken every time it came in contact and bounced off the vegetation to ensure accuracy of results based on average time and speed. For the most dense vegetation patch, even though the biggest and the smallest plastic objects reached location B with a similar speed, upon interaction with the simulated vegetation, the speed decreased rapidly. Even though the patch of vegetation was unable to block the biggest object, it had an efficiency of 85% when reducing the kinetic energy. For the medium dense vegetation, the initial speed achieved to reach point B was quite close for all the test subjects. The biggest object was the slowest and the smallest one was the fastest. The differences in the kinetic energy at point B to the kinetic energy at point C was quite similar as well. The efficiency at which the kinetic energy of the plastic objects decrease also shows a similar trend. On an average, this patch of vegetation decreases the kinetic energy by 79%. Just like the most and medium dense vegetations, the speed obtained by the different plastic sizes were quite similar. From the table, the least dense vegetation patch lets the object speed up quite fast even after contact. The efficiency at which the kinetic energy changed was quite different from the trends seen before. The smallest object has the least efficiency of 49%. The efficiency increases as the size increases, but it was soon seen to decrease for the two biggest sizes of plastic. From this study on the flow of floating plastics in the river system, we got a better understanding of the problems and the effects of it. From the literature review, a perspective was gathered on the factors affecting the flow of the buoyant microplastics and how it causes accumulation over time. Upon using vegetation, it was seen that it affects the velocity of the plastic and decreases its kinetic energy while blocking the object. Though it depends on the area, the concept of riverbank vegetation can be used every few kilometers. Based on the basic concepts of physics, slower velocities at the banks make it easier for the floating or plastics to be captured without disrupting the river ecology and habitat. To summarize, the study will help the engineers in the future to design and produce more resilient types of vegetation patches. This will be low cost and environment friendly engineering structures which will help to trap and remove floating plastic waste in the river system. Thank you.